All right. The mic's good? Yeah. All right, so let's start. As Professor Troyer is not around this week, I'll be giving the lecture, and he'll be back next week. All right, so today's topic is the hardware of your PC. In case you're asking why you should think about hardware in a programming course, the answer is pretty simple. You're programming for this hardware, and if you want to write any decently performing code, you should know what the hardware is doing with your code. All right. So first, we should think about what actually happens if you execute a code. You write this code in some high-level language, like C++ in this course. Then the compiler will translate this to machine language, and the computer will... Sorry, is there problems?
Microphone is not in the right position.
Oh. Okay, better now?
Yeah.
Right. Seems like I have a non-standard head. Right. All right, so you run your compiler over your C++ program, and the compiler will translate the C++ code into machine language. And the computer will only see this machine language that the compiler produced. It will never see your C++ code while executing the code, right? So if you now want to write a fast program, you should first understand the limitations of your hardware. And second, you should understand what the compiler does with your code. So this week, we will mostly look at the hardware part. We will look at what are the main components of your PC and understand what they can do and what they cannot do. So that's your computer in a very simplified block diagram. We basically have the memory on top, and all this down here is what is contained in your CPU, in your central processing unit. So what you typically think of is the execution unit that's actually executing your code. But for that to happen, there's some stuff around. So first, your code in machine language is lying in memory. And then the CPU, as a first step, has to get your code from memory. Then it will decode the instructions in your code and send these decoded instructions then to the execution unit. And then your code will work on some data typically. And so it needs to get the data from memory and write it back to memory. And there's several caches in between that we will talk about later on. So let's first concentrate on the CPU part. That's again consisting of several components, as you just saw. First, there's a memory controller which manages loading data and code from memory and storing the process data back to memory. Then within the CPU, there are registers that can store some numbers, so either integer or floating point numbers. From the programmer's point of view, you can set values into the registers, or you can load some data into the registers and store it back to memory. Then in the central execution part, there's the arithmetic and logical units, which perform the actual arithmetic operations or comparisons, as the name already suggests. They can operate on values that are already in the registers. And depending on the architecture, some CPUs can also directly operate on contents that are in the memory, but this is a lot slower. And then there's the fetch and decode unit, which gets the next instruction from memory. It interprets the instruction and depending on the value of that instruction, it decides what to do next, and then gives the instruction to one of the parts of the execution unit that can do something with that instruction. So that's the broad part of what is in your CPU. You should note that the reality is far more complex for modern CPUs, and we will have a few examples of that later on. So first, I already talked about this machine code. So as I said, the CPU gets your compiled instructions from memory. These are in machine code, which is basically just numbers. And depending on these numbers, the CPU knows what it should do. So just looking at these binary numbers doesn't tell you anything if you're not very, very experienced. So probably you will never in your life look at this compiled machine code. But what you might want to look at is a one-to-one translation of this binary machine code into something more human readable, which then is written in assembly language. So as this is a direct translation of the machine code, it depends on the CPU that you compiled your program for, meaning it's not portable. If you take this ASM code and go to a totally different computer, put it in there, run it through an assembler, it might not run because it's a different architecture. So most often you do not want to write assembly language, but you might want to look at it to see what the compiler actually did to your code. And so what you might see if you look at some assembly code is some load and store instructions that put data from memory into registers or vice versa. And then, of course, the arithmetic and logical instructions that perform on the registers. And then the execution control that can jump or branch to another instruction. Otherwise, a program could never have any if or while parts, but would just execute sequentially whatever you write. And so this jumping and branching is rather important for the program control. Then a rather essential part in modern CPUs is pipelining, which is used to speed up the execution of code. So in general, a CPU needs several cycles to process one instruction you gave it. So that would be rather slow if it first needs to get one instruction. That's the fetch stage here in this example. Then it needs to decode that instruction. It needs to fetch the operands into the registers, execute the actual instruction, and then write back the results into memory or some other registers. So in this example, that would be 5 cycles, and only afterwards you could start doing something new. Now, pipelining tries to identify instructions that are independent from each other and already start a new instruction before the previous instruction has finished executing. So after fetching instruction 1, it will immediately go on to fetch instruction 2, even if it hasn't fully executed the first instruction yet. And so if this runs nicely, you can produce the result of one instruction every cycle. So to the outside, it looks like the CPU only needed one cycle to execute one instruction. Because if you look at the output, you will write back instruction 1 here, and then in the next cycle instruction 2, and instruction 3 in the third cycle. Now for a very simple example of that, imagine a loop that's just adding 2 arrays into a third array. Now all these operations within this loop are totally independent of each other. You can easily compute the sum of the second 2 elements of each array without knowing the result of the first addition, right? So after putting several of these summation into one iteration, you can easily do these 4 instructions and in a pipelined way so that you get one addition result each cycle. Now why this unrolling? Well, otherwise after one addition you would be back to this check of the loop count. And this check, of course, needs to know what the previous iteration was. So this is basically a serialization point at which you need to wait for the result of the previous adding 1 to the iteration counter before you can do the actual check. But if you now make this loop fatter and put more additions within one loop iteration, you can do all the instructions in here independent of each other. Is that clear? If it's roughly clear, we can look at an example. So we have these examples in the repository. The first one is very simple. It's a code that just adds 2 floating point numbers. So let's look at this example. The second example is what you've just seen, the loop adding 2 arrays. Now let's look at these codes. Is that large enough to see it? Yes? Good. Okay. So first the simple add. It's very simple. It's a sum function that gets 2 double arguments and returns the sum of these 2 doubles. Okay. Now let's compile this. We want to save the temporary files, so we can look at the assembly code. We only want to compile, not link. We want to optimize. All right. Now we have the assembly code here. So you have some header which contains the name of the function, which you don't need to care so much. And these 2 lines here are the actual code executing your function. You have 2 floating point values in these registers, xmm0 and xmm1. So registers in this assembly language are denoted by the % in the beginning. And you add these 2 single double numbers. The result will be put in the xmm0 register, and afterwards you return. Very simple, if you know what to look at. Okay? That's clear? Basically, we have a very simple function, 1 addition, and that translates in this case to 1 assembly instruction. So now let's look at the loop. Okay, we get 2 input arrays, B and C, passed via const double pointer. We have a for loop over good 10,000 elements, and we write the result of adding the ith element of B and the ith element of C into the A array. So let's compile this. I'll tell you later on why I add this argument here. Let's look at the code. All right. Again, some initial setup, and then here we have the main code. First line, we load with this morph statement from memory into the register XMM0. Second line, we add the contents of this memory location here into the register. And third line, we store the result again with a morph instruction back into this memory location here. So this register RAX contains a loop counter, so it tells you what memory location, and these RSI, RDX, and RDI registers contain the pointers to the A, B, and C arrays. So afterwards, we add 8 to the iteration counter because the double has 8 bytes, so we proceed by 8 bytes. And then we compare the value of the iteration counter with 81,920, which is 8 times our iteration count. So if these two are not equal, we have not done all the iterations yet, and we will jump back to this label L2 here and do the next iteration. Otherwise, we will return from the function. Okay? Just an impression of what you can see, how this assembly code looks like. Now, here we just have one of these iterations in every loop iteration, so it's very hard to do pipelining on this. So let's tell the compiler to unroll this loop with -f unroll loops. Look again at the code. Now you see the loop is very long, right? It's a lot more instructions. But basically you can see the same thing, just repeat it over and over again. You load the first argument of the addition, you add to another memory location, you write back the result. But now you immediately go on and do the same thing on the next element using different registers. The third element, fourth element, fifth element, sixth element, seventh element, eighth element, sorry. And after doing 8 additions, we increment the loop counter by 64 bytes, 8 times a double. Check the loop condition, and if we haven't reached all iterations yet, we will jump back to the start of the loop. Otherwise, we will return. So now we have unrolled the loop into putting 8 iterations into one iteration, and the processor and all these additions are independent of each other, so the processor can nicely pipeline this. The downside is your code became a lot larger, And that may again have a performance impact. So it's not always better to do this. All right. We'll have a third example later on when I also tell you why I put this no tree vectorize option there. Okay. Yes.
I wanted to ask if the maximum of I has to be divisible by 8, or
yeah, otherwise you could split off the last part and put that after the loop. So in principle it's possible, but it will require even more code if it's not dividable. And the whole thing, of course, gets more difficult if you don't hard code the number of iterations, but it's a variable how often you will loop through this array. More questions? Yes?
Why did it do 8 operations and not more?
Good question. So in the end, as I said, it's a compromise between the size of the code, which may impact performance, and the potential for pipelining. So the compiler decided that 8 is a good trade-off. You will probably not find many CPUs these days with an even longer pipeline, but you will never know without trying out all the different unrolling chunks. But in general, the compiler is not too bad in this, if you tell him what CPU you're running on. Okay? Any more questions? All right. So we already saw that this loop is a problem for pipelining. And you can't always rely on me telling the compiler to unroll all the loops. As I said, that might have a severe performance impact again. So what modern CPUs are actually doing is they're just guessing, and they start executing some instructions that they think will be rather likely. And if they guessed correctly, they can have the pipeline running on, producing results every cycle without any pipeline stall. Of course, if the guess is wrong, then they produced wrong results, but that's not too bad because they haven't written the results back into the memory yet. So it's still within the CPU. And so if it turns out that they executed the wrong branch, they will just throw all the wrong results away and start again at that point where they took the wrong branch. And into this branch prediction, today a lot of development effort is put. Because if you can feed the pipeline nicely and have it roll on, you will have a much faster code than if you need to wait and have these pipeline stalls. Okay. Is that clear so far? Otherwise, ask questions. Okay. So I showed a very simplified version of your computer. This is a slightly less simplified version of only the CPU part. So let's have a look of what is actually in there. What you would usually think of a CPU is actually mostly this part here, from that level down to this level, which is actually the real execution unit. And you see that this execution unit is split into several independent parts, or ports as they are called here, which may work on independent parts of your pipeline. Above that, of course, you have to have a scheduler that tells the CPU which port should execute what instruction. So here you have 3 ports that do what you would usually call the arithmetic and logical operations, so actual calculations. And here on the right hand you have 3 ports which talk to the memory controller. So they take the task of loading data from memory and storing it back to memory. Now before these parts here can jump into action, they need to have some instructions. So that's what's going on up here. So the CPU can load the instructions from memory, via these caches. We will talk about these later. Then there's a pre-decode step where it will start decoding the instructions. Then we'll put it into a queue, and there's several decoders that can decode in parallel. And then very important is this part here, which can actually reorder instructions. So depending on what data is already in the CPU, it might make more sense to do something that comes later on in your code and do it first. So that's the so-called out-of-order execution, which also helps hiding latencies from the memory and so on. All right, so we will talk about some parts of this later on. That's just to give a general impression. Before we dive into some parts more in detail, one thing that's often mentioned about CPUs is this famous Moore's law, which you might have heard about. There's many versions of that. The original version was the number of transistors on a chip doubles every 18 months. Now, you might have heard that Moore's law is actually saying CPUs are getting faster. That's not entirely true, and still there's a lot of truth within this, because more transistors on the same chip means the transistors themselves get smaller. And smaller transistors means you have shorter distances between the transistors, so you can faster send signals around between them. And on the other hand, smaller transistors means there's fewer charges representing 1 bit, which means you can faster shuffle these charges around. And so the switching is also faster. So in the end, Moore's law implies that CPU speed should also increase exponentially. Now this has remarkably worked for 30 years. The question people are today asking is, how long can it continue? So today you have some prototype chips, for example, at 10 gigahertz, where the insulating layers are only 4 atoms thick. Now it's clear if you want to shrink this further and further, at some point you will have only 1 atom, and you can't put half an atom there. So there's some wall you will hit at some point. But that's why we're here, because then, if the hardware is not getting faster, then we should make the software faster, right? So that's a plot for supercomputers, which shows that Moore's law worked pretty nicely for 2 decades in this plot. There's this famous list of the top 500 supercomputers in the world. And the top line is adding the processing power of all these 500 systems together. You get the total performance of all these systems, and this is nicely growing. So note on the left-hand side you have a log scale. So each step here is meaning the performance is 10 times more than on the previous line, right? So over these 2 decades, we went from something around 1 teraflop to more than 100 teraflops. And the same thing is true if you look at individual systems. That's the number 1 in the list and the number 500 in the list. And so you see that nowadays, the number 500 system is about as fast as the number 1 system 5 years ago or something. Okay, so talking about Moore's law, you can say there's also a Moore's gap, meaning if you look at the performance of a single chip or a single processing core, you will see that there was actually some transition to a smaller growth. So the number of transistors on the chip still growed exponentially with the same rate, but the serial performance is not growing as fast as it used to. So you can also see this if you look at a few models. So each of these CPUs is one representative from some year, and then 5 years later, and again 5 years later. Now this table here is claiming that the chip still got faster in this benchmark. And I just said the serial performance did not grow as fast as it used to. Now, what's the crucial difference here? Any idea?
Multi-core?
Yeah, multi-core chips. So in the past, the performance of the CPU was mostly increased by increasing the frequencies. So we started with a few megahertz clock cycle in CPUs, and nowadays we have several gigahertz. And this, of course, makes the chips faster, but increasing the frequency is very expensive in terms of power. So the power consumption in this period raised a lot. And if you try to raise the frequency even more, you will need a huge block of ice on your CPU. And it's very hard to even get the heat from your CPU into this block of ice because it's producing so much power that it's even hard to get out of the silicon, right? So that's the reason why in these 5 years the frequency growed a lot, whereas today's, well, okay, not quite today, but almost today's chip has a lower clock frequency than this guy, but it's still a lot faster. So how can we do this? The main reason you already said, today we put 8 or more cores onto a single chip. And if you add up all the processing power of these different cores, then you get a nice performance enhancement. But of course, if you only have a serial code, that doesn't help you. So we will talk about this later. There's also improvements in pipelining and branch prediction, as I said earlier on, and caches have become a lot more important than in the early days. So, but parallelism is the main point. So let's have a look at a few examples of parallelization. Even if you will not learn too much about that here, there's separate lectures for that. So one thing each of your processors has is this SIMD vector operations, which go under the name of SSE for streaming SIMD extensions, or nowadays AVX for advanced vector extensions. And the overall principle is always the same. You have the same instruction, but you perform the same instruction on several data bits, several words, several independent variables. So one simple example for that is adding 4 pairs of floating point value in a single operation. So you have this vector of 1, 2, 3, 4 floats here, and you want to add to each of them one of these floats. And now there's an SSE instruction for doing that, and a rather recent Intel Sandy Bridge CPU can execute this one instruction doing 4 additions within one cycle. So that's pretty neat. If you have a code that's actually doing several operations, a single operation on much data. So how can you use that? So the good part is the compiler can automatically generate this SIMD code. And now you see again this tree vectorize option that I promised you to talk about later on. So if we again go back to our beloved loop add example, if you remember the loop, we're actually doing something that's very SIMD-like. We're adding two huge arrays which are independent of each other into a third array. So this could easily be parallelized with this instruction I sketched in the presentation. And so let's now tell the compiler that it's allowed to vectorize my code. Let's get rid of the unrolling, otherwise the code might be a bit complex. And let's look at the ASM code. All right, there's some initial setup, and this here is the actual loop. So the first part are several memory operations which prepare our vector registers. So these XMM registers are SSE registers which can actually hold several variables. And so this morph SD operation loads into the lower part of the vector, and the morph HPD loads into the higher part of the vector. And after this loading, we can, with one single instruction, load two doubles. If I had a loop over floats, it could add 4 float variables at once. After this single vector operation, it will again store the results into memory. Now it has added 2 variables at once, so it can add 16, so 2 times the size of double to the loop counter. Okay. Any questions? No? Very good. Apparently you understood everything. Right. So we saw that the compiler can generate SIMD code. Unfortunately, to generate optimal performance code, that requires a lot more care. You saw this whole bunch of morph operations for loading and storing the values from the memory into the registers and back. And that, of course, takes a lot of time. So if you want to get nice performance, you can optimize a lot on that to put all the loads into a single operation and so on. But that requires care in how you store your variables in memory and about alignment. And of course, the compiler is totally lost if there's data dependencies within the iteration. So if you add the result of the previous addition again to something else, then there's no way to do this within a single vector operation. So there's a lot to do for the programmer still. In this course, we will not talk about that, but there's this high-performance computing for science and engineering, which you might take in a later semester. And there, this is an important part. All right, so that were the SIMD units, which are still living within a single CPU core. But now we already mentioned these multi-core chipsets. So we basically have several CPUs on one single chip. And so you can parallelize your code by giving some work to each of these CPUs. And all these cores you have on the chip, they can access the same memory. That's why this model of parallelization is called a shared memory architecture. Now for high performance computing, you additionally have a lot of different nodes, each node having its own memory and a set of CPUs. And now these CPUs do not see the memory of each other. So you have here one node with, say, 4 CPUs and some memory. And if they want to access data from this node down here, they have to explicitly ask the other node to send that data over the network. Now, as you can imagine, that additionally requires some work from the programmer. And so these parallelization schemes and how to optimally use them are again taught in this high-performance computing lecture. So I don't know if there's some time in the end of this lecture we might have a short glimpse into parallelization. But before you can write a fast parallel code, you should be able to write a fast serial code. And that's what we will talk about in this lecture. Now, in the last years, there's one more concept arising in scientific computing, that of the GPUs, where GPU used to stand for graphics processing unit, which you might have used to play some computer games, for scientific data processing, I mean. Now these GPUs have become very fast and can work very nicely with floating point numbers. So often you can get a 3 times speed up by replacing one of these multi-core CPUs by one of these GPUs. That's an example here of one of the flagship products of NVIDIA, which is used in the most modern supercomputer we have down in the Swiss Supercomputing Center in Lugano. So that single device here, which you could put into your PC on its own, has almost 3,000 cores, and this single device can give you a performance of almost 4 teraflops, which is a supercomputer of a few years ago. Now, programming these guys is again a challenge of its own. Basically, they are huge SIMD units. So if you, in the previous slides, thought about how you could write your code so it does 4 additions in once, now you should think about hundreds of additions of totally independent data, which could be performed in parallel. And for doing that, there's again different programming environments, most importantly CUDA by NVIDIA and OpenCL, which is an open standard. So again, that's part of the high performance computing lecture. Let's first concentrate on the single core. So here we have a summary about this first part of the lecture where we talked about the CPU, the central processing unit. So the bottom line is everything is complex and it's getting even more complex over the years. So nowadays you have this branch prediction and out of order execution done in hardware. So it's becoming increasingly hard to tell what the CPU is actually doing with your code. Then you have these SIMD units, which offer a slightly different computing paradigm, which you have to use if you want to get the most performance out of your CPU. And additionally, multi-core architectures with non-uniform memory access, which makes things even harder. So not every processing core can access every part of your computer's main memory with the same speed. Right. So it's hard, but all right. We're tackling one part after the other, and if you have a bit of experience with that, you can get very fast and decent performing code. So that's about your PC, which should be the main topic of this lecture. We also had a few short glimpse into high performance computing, where you then have parallelization on many different levels. You have these SIMD units, then you have several cores on one chip, with each of these chips, with each of these cores having its own SIMD units. And then you have a supercomputer which consists of many, many nodes, each having several CPUs, right? And the future is getting even more hybrid and complex, because we will likely have a lot of these GPUs additionally in each of the processing nodes. Right. So that was the part about the CPU. The second part of the lecture will be about the rest of the system, which unfortunately has not gone as fast as the CPU. So there might be a Moore's law for these other components too, probably not for your hard disk. But it's not increasing as fast as the CPU performance. And that adds problems again for writing fast codes, and that's what we will look at in 15 minutes, I guess. So let's have a break and then continue. All right, so if everyone's back, did you have any questions that popped up during the break? No? So yeah, that second part of the break is devoted to all the rest besides the CPU in your computer. Most importantly, the memory, which is essential for the speed, right? So we know that the transistor density doubles every 18 months as long as we have Moore's law. And the PC speed doubles roughly every 2 or 2.5 years. So today's PCs are basically as fast as supercomputers were 10 or slightly more years ago. But at the same time, supercomputer speed doubles every year, so your PC will not catch up with these big machines. That's not so much of a problem. A bigger problem is that the rest of your system does not catch up with the performance of your CPU. RAM speed does not increase as fast as the processing speed of your CPU. And about disk speed, you don't even need to think about. That's extremely slow. So here's a plot comparing the performance of a CPU versus the performance of two different memory types. Most importantly, there's the DRAM, which is what your main memory is built out of. So if you now compare the line of the main memory's performance and that of your CPU's performance, you see there's a huge gap opening. And now there's some memory types that are slightly faster. They're still not quite keeping up with the CPU, but a lot better than the DRAM. So what's the difference between them, and why is your main memory still that lower line? So you should know that there are different types of memory, or random access memory, RAM. First, there's the so-called SRAM for static random access memory, which is very fast to access. Unfortunately, it's also very expensive. So if you ask anyone to put a few gigabytes of that into your computer, you will not be able to pay it. So in SRAM, the data is stored in the state of the transistors, which are in a flip-flop switch. and the data stays as long in there as there's power. So that's the reason why that's called static memory. Compared to that, there's the dynamic random access memory, DRAM, which is a lot cheaper than the SRAM, but unfortunately also slower. So in DRAM, the data is stored in capacitors, which will, of course, discharge if you just let them stay somewhere. So they need to be recharged regularly, and that's the reason why this type of RAM is called dynamic RAM. Now, we have one type of memory which is very fast and very expensive, and one type which is a lot slower, but also a lot less expensive. So the trade-off you'd have is putting a lot of the fast, a lot of the not so fast, but rather cheap memory in your computer, and not so much of the a lot faster, but also a lot more expensive memory. Now the DRAM is mostly used for the main memory, as I said, and so over the years there are several variations on that have emerged. It's not so important to know exactly what it is, but as you might have run over all these different acronyms, it might make sense to at least mention what they are. So there's this SDRAM, synchronous dynamic random access memory, which is basically DRAM, but the clocks of the memory are synchronized with the caches and hence with the CPU. And that allows faster reading. Also there's DDR-RAM, double data rate, and interleaved memory systems, which means you divide your memory in several memory banks, and you can read in parallel from these different banks. So DDR SDRAM and interleaved memory systems is what you usually have in the most current computers. But they're still far slower than the typical SRAM, or far, far, far slower than the typical CPU. So what do? You have a very fast CPU, which could process a lot of data, but it is way faster than the memory from which you need to get the data. So if you just have that very slow memory and a very fast CPU, the CPU will basically die of boredom while it's waiting for the memory to give new data, right? So what do you do now? Well, you add some portions of this faster SRAM memory in between the slow main memory and your CPU. And that's the so-called caches. So in a typical system nowadays, you have many gigabytes of this slow dynamic random access memory. Then you have, say, a few megabytes of fast and expensive level 3 cache, which is a lot faster than the DRAM, but still slower than the CPU. Then you have even less of even faster memory, which is called the level 2 cache. And this is typically built into each CPU core, so it's very close to the processing unit. And then you have even faster, but also more expensive and therefore slower level 1 cache, which is typically split between instruction cache and data cache. So now you see you have very fast memory, but it's very slow. And then you have a lot of memory. Wait, what did I say? So you have very fast memory, but it's very small. And you have very much memory, huge amounts, which are very slow. So if you now look at your problem and look how much data are you processing, if this data is only a few bytes or a few kilobytes, the whole data will fit into the fastest cache and the program will run very fast. On the other hand, if you're processing lots of gigabytes of data and only use each of that once, so you load it, you process it, you store it away, then this will only fit into the largest and slowest memory. And so the whole speed of your code will be limited by the memory bandwidth of your slowest memory, which is not good, of course. So here's a quantification for one specific CPU, but the rough numbers are very similar for all up-to-date systems. So you have this fast level 1 cache, which can basically give you data within 2 cycles. So that's almost as fast as the CPU. Then the level 2 cache already takes some tens of cycles. The level 3 cache almost 100 cycles. And if you really have to go and get something from memory, you need to wait for 300 or more cycles. So if you imagine this situation where you get 2 pieces of data from memory, do one operation on them and write them back, you tell the memory controller you need that data, and then you will do nothing for 300 cycles. Then you will do one operation, tell the memory controller to write it back, and maybe get the next data, but then you will again wait for 300 cycles. So of course that's not optimal. All right? So that's why you should use the caches as much as possible. So how do these caches work in practice? Right. So the CPU requests one single variable, one word. That might be 4 bytes if it's an integer. And that needs to be read from memory. So the memory controller will request it. But it will not only request that single word, but a whole so-called cache line, which will typically be 64 bytes of consecutive memory. And that consecutive memory will directly be read from memory and stored in the cache. And then the cache will send the first word, which was requested by the CPU, directly on to the CPU. So if now the CPU for the next operation wants another word, the cache will first check, have I already loaded that in the previous cache line? And if it has, it can immediately respond and give the CPU what it wants. If it's not in the cache yet, then, well, it needs to again go to memory and load another cache line. So if you only load cache lines, load data from memory, at some point your cache will be full and you can't load anything else. And so the oldest data will be thrown away from the cache. It's still in the memory, so it's safe. And then it will be replaced by what the CPU needs next. So given you have these cache lines and you always load some chunks of consecutive memory, it's a very good idea to work on data that is as close together as possible in memory, right? So if you load the first part of a cache line and then some variable which is just next to that, then you can fully use that cache. Whereas if you do some random access in your main memory, and you read something from there and then something from totally different location, then the cache is useless. So that's why the so-called locality of your memory references is very important for speed. Okay, are you with me at this point? Very good. So there's several types of caches. There's one very straightforward implementation if you're trying to build a cache, which is you compute the location where something will be stored in cache directly from its address. So if your cache has place for 4 cache lines, say, then if the remainder of dividing the address by 4 is 0, you put it into the first part of the cache. If the remainder is 1, you put it into the second part, and so on. And so after 4 of these cache lines, you're again back to something divisible by 4, and it will be put into the same cache location as your first cache line. Now this is very easy to implement and very cheap. The problem is if you're now going through your memory in a stride, so with steps that are exactly 4 cache lines, you will load the first cache line, then you load the 5th cache line, which will be put into exactly the same cache location as your first cache line. And then the 5 plus 4 is 9th cache line, which will again overwrite the thing you did before. So you will only use one part of your cache, and everything else is useless. So this directly mapped cache is very simple to implement, but it has this risk of the so-called cache thrashing, and therefore it can have quite an impact on performance. So the other extreme solution is the so-called fully associative cache, where any cache line can be put into any location within the cache. So by that, you avoid this type of cache thrashing, and you never need to throw something out of the cache that is not the oldest item. But it's also very expensive. So again, you have a very cheap solution and a very expensive solution. The cheap is slow, the expensive is fast. What do? Well, you make a compromise, and that's the so-called n-way associative cache, which is what you actually have in basically all modern systems. And there, each address can be put in one of several locations, but not all of them, which would be the fully associative cache. All right, and by that way, so typical today's caches are something like 8 ways associative or 16 ways or something. By that, you have to have a very special access pattern to have this problem of cache thrashing, and still the cost is not too high. Okay, that's the basic explanation of the cache. You already got the exercise of testing your cache and writing a program on how to measure how many different cache levels you have and how big they are. So now you got the explanation of what you are measuring, and I hope you're able to do that exercise until next week. So if you're really keen and the first part was too simple, then try to see in your data if you can see the associativity of your level 1 cache. That's a bit more of a challenge. Okay. So any questions on the caches? No? Right. So that was one part of the memory system. Unfortunately, everything is even more complicated and hence even slower. Namely, there's a so-called virtual memory system, which is a solution to 2 problems. Namely, first, what happens if you have several programs that run on the same machine? Obviously, they need some portions of memory, and they should not use the same memory, right? And second, what if we need more memory than our system has RAM? Well, we can say we ran out of memory and crash, but that's not such a nice solution. So what we actually do is put in a layer of so-called virtual memory. And this means that your program will run in a so-called logical address space, or virtual, which is totally independent from the actual physical part of your memory. So if you print out the address that is stored in some pointer in your code, there's no way to tell where on your chip actually the corresponding data is. But there's a translation layer in the hardware that will map this logical address within your code to a physical address within your memory chip. Now that helps with the many programs in one memory, and is the first part of the solution to what happens if you have more memory than RAM. The second part to that second problem is using swap space. You have a huge disk connected to your computer and you can store a lot of things there. So just put some of the logical virtual address space onto disk and store the data on disk. So of course this is extremely slow if you need the data, because then you first have to go to disk and load that stuff into memory and then get it from memory, which is still slow. But at least you have the problem that you don't need to crash at the point where the code requires more memory than your computer has, right? So how is this virtual memory implemented? Well, you organize your address space, so your physical address space, the real memory you have, into so-called pages. That might be 4 kilobytes or a few megabytes on more recent systems. And now you have this hardware translation of logical virtual addresses into physical address space. Now that translation is done with the so-called page table. So it's a huge table where you say, okay, that you have one table for each program running. And so this address here refers to this page in your memory. So if you want to access some data in memory, you will access the page table, look where this address is actually stored physically, and then go to the actual memory location, or to disk if it's paged out. So the problem with that is if this page table is just somewhere in your memory, then you first need to read from memory the page table, look into the page table, and then again go to the memory to read the actual data you wanted. So the solution to that is again a cache. Now this special cache only for the page table, which should be as fast as possible, has a special name. It's a so-called translation look-aside buffer, because it's used for this translation from logical to physical address space. And again, you can only store parts of your page table in this buffer if you have many different memory locations in your code. So again, it's important to have these memory references as close together as possible, as local as possible, because then you will have fewer entries in the page table. And by reusing the same entries, you can reuse the parts that are still in this translation look-aside buffer. So the worst case, if you want to read something from memory, is you say, I have this address, I want the corresponding data. So you say, tell your memory controller, get me that address. It will go to level 1 cache. It will not be there. That's called a cache miss. So it goes to level 2 cache. If it's also not there, another cache miss. It goes to level 3 cache. Cache miss, no data. All right, then we need to go to physical memory, and to know where we have to go to, we look into the translation look aside buffer and get the page table entry for this address. Now, if this entry is unfortunately not in this buffer, then we first have to get the corresponding part of the page table from memory, wait 300 cycles. Then we look again into the new entry, and it tells us, well, I have swapped that out onto disk. Bad for you. Now you go to disk, say, okay, I want that part of the swap file back read into memory. For that, I need to create and initialize a new page where I can put the data in. Then wait for the disk to give me the data, put it into memory, and then load the value from memory. Another 300 cycles. But that doesn't matter if you had to wait for the disk. So that's ages in the reference frame of your CPU speed. And so the bottom line of the second part of the lecture is really try to reuse data as much as possible. So once you have something in your registers, do as much as you can with it. And only when you're done with that part of the data, write that back into memory and get the next part. All right. Questions on this part about the memory system? So here you have this small sketch. The CPU is up here. You have this hierarchy of caches. You have the page table, which is stored in another cache, the translation look aside buffer. And then there's memory and the disk for swap space. Any questions? Seems not to be the case, so I guess we can finish for today. And next week, Professor Troyer will be back and start with some more advanced C++, like templates and stuff, I think.